Okay, welcome to tonight's lesson. So still under vibrations and looking at waves, and this is lecture 5. My name is Hamded. Yeah, so we're going to start first by looking at what a wave is. From there, we'll look at the types of waves. Then apart from that, we'll look at the frequency, the amplitude, and the wavelength of a wave. Okay, so let's define what a wave is. So a wave is simply just any disturbance. Yeah, any disturbance that transfers energy. Yeah, so waves are produced by vibrations and oscillations. So while there are no vibrations or oscillations, we don't expect to have a wave. Yeah, so a wave is simply just a disturbance that transfers energy. So waves, like I said, they are produced by vibrations or oscillations. Yeah, so we're going to discuss what we call mechanical and electromagnetic waves. So between mechanical and electromagnetic, there is one which uses which always needs particles for it to be for it to travel in short. And then there is also one which do not need particles. We're going to look at that, which do not need a medium. Sorry, not really particles, but a medium. Okay. So we have. Let's look at the types of waves. We have what are called transverse waves. So transverse waves are simply just waves in which particles vibrate perpendicular to the direction of travel of a wave. So examples are electromagnetic waves. And then we have water waves, and we have waves on the stream. Okay, so these types of waves, if let's say for instance the direction of a wave is this side, this happens maybe for instance when you drop something on water, on still water which is not moving. And when you drop something there, you discover that you have a wave. Maybe it will start like this. It will be here. Just after a few seconds, you see it there. Just after a few seconds, you see it there. And then to keep on moving like that. So you discover that these particles will be vibrating like this as it is going this side. The particles will be vibrating like this, going towards the direction of the wave. Okay, so this type of a wave this is how we can simplify its direction. So you can see that the particles are vibrating, going up, going down, going up, going down, perpendicular to the direction of the wave. Okay, let's also look at what are known as longitudinal waves. So longitudinal waves are simply just the opposite of transverse waves. Since we said transverse waves have particles which vibrate perpendicular to the direction of the wave, for longitudinal waves we discover the particles. We have to understand that the particles will always vibrate parallel to the direction of the wave. So this is exactly what we are talking about. Imagine you have a wave, like this wave on the stretched and compressed spring. When you compress this spring and then you stretch it, you discover that you have certain waves that will be moving like this. You have at one point the spring is going to be compressed, and then you also have a part that is going to be stretched like these two parts. Then at these 2 points the spring will be compressed. So what you discover is that this compressed part will be moving. It will start from there, it will be going this side. So the particles will be moving. So you discover that this compressed part at one point it will be here. The other point you see it somewhere there. Just a few seconds you see it somewhere this side. Then after a few seconds you see it coming back this side. So you discover that this is a proper way that can show us that these particles in this spring are simply moving this side, and then after going this side, they also, after reaching the end here, they start coming back this side. And when you look at the direction of this wave in this spring, it is still the same direction as it is going this side. the wave is also going this side. As the compressed part is coming back this side, the wave will also start coming back this side. That's what we mean by moving parallel to the direction of the wave. So let's look at what are called mechanical and electromagnetic waves. So when we talk about mechanical waves, we simply refer to those waves that require a medium for them to be transferred. So these kinds of waves, like sound waves, sound cannot be transferred where there is no medium, where there is nothing, in short. Sound is always transferred using using a medium, in short. Okay. And then we have what are called electromagnetic waves. These kinds of waves, they don't require a medium for them to be transferred from one point to another. Yeah, so this is what I'm just trying to talk about. So electromagnetic waves do not require a particle or a particle medium to transfer energy. And then mechanical waves require a particle medium for them to transfer the energy from one point to another. And then the example that has been given here is sound waves. Alright, let's quickly proceed. Let's look at the characteristics of waves. So characteristics of waves, we have the distance. A wave, the displacement. So we have what is called the displacement. So a wave can be displaced from one point to another. And this displacement can easily be defined as the distance that is moved in a particular direction. So the same way you define displacement in other topics, that's the same way you define displacement even on waves. It is mostly represented by the letter x, and it is defined as the distance moved, the particle moves in a specific direction. That is called the displacement. So apart from the displacement, we also have what is known as the amplitude. So the amplitude, in some books, it is represented as A, and then the amplitude is represented by A, and then some represented by x naught. So all these two symbols represent amplitude. So this is just the distance of maximum displacement, in short. Remember when you talked about a spring, if you have a spring that is being attached to the wall like this, you discover that as you stretch it, and then you stretch it going this side, and then you release it to go back, it will go back, and then the second time when it comes back this side, when it goes back this side, and then the second time it will come back this side on its own, it's going to pass the point which is called the equilibrium point. So the equilibrium point is a point where the displacement of this spring or the particles in the spring is actually equal to 0. Then when it goes this side, it's going to move a certain distance, and then at one point this side, when going this side, it's going to have the velocity which is equal to 0 at maximum displacement. The velocity is going to be closer to 0. As a result, at this point, the mechanical energy, in the equation of the mechanical energy rather, the kinetic energy is going to be equal to 0, and the potential energy is the only one that you are going to have. And then at this point, the potential energy will not have the value x. We know that it's given by kx squared, half kx squared. That is the value, the formula for potential energy. So this x, which is just the distance moved by the spring, at this point we can have x1, another point we have x2, but at this maximum displacement we count that to be the amplitude. So the amplitude, so at that point you discover that the formula changes to half k a squared. Why do we write a? Because we know that a is simply just the maximum displacement a wave moves. So this is exactly what we are talking about when you talk about the amplitude. So amplitude is simply just the maximum displacement that the wave has moved or is going to move. And then apart from that, we can also talk about what is called the amplitude, the period. So the period is simply just the time taken for a complete wave. So period is mostly represented by the capital letter T. So period is simply just capital letter T, and it is defined as the time taken for a complete wave to occur. Yeah, so that's the period. And then apart from that, we also have what is known as the frequency. So the frequency is simply just the number of waves passing through a point per unit time. So the number of waves, so the frequency can be defined as the number of waves passing through a point per unit time. So if the frequency can be written in this format, we know that the period is simply just equal to 1 over f. So meaning when you say 1 over n over t, this can also be written as t over n. That is the period. So you don't have to forget about these small simple formulas. You have to master them. Okay. Yeah, so the next thing we're going to look at is we talked about the frequency. Then the next thing we'll look at is the wavelength. So the wavelength is simply just the distance covered by a complete wave. Yeah, so a complete wave, when a complete wave covers a particular distance, we call that distance to be a wavelength. So it is also the distance between two successive crests or trough, and it is the distance between 2 points vibrating in phase. So when we talk about 2 points in phase, it means that their troughs or their crests are aligned in the same. In short, they are in the same line. So we're going to discuss phase difference in the next slide that we're going to have, in the next lesson that we're going to have. Yeah, but for now, just not to say it is also the distance between 2 points vibrating in the same phase, or the points that are in phase. And then, okay, so what they mean by wavelength, if you have a wave like this, you have a wave moving like this. So if this is a trough, which is just the minimum distance of a wave, or the minimum should I say amplitude? Okay, let me just say the minimum distance the wave covers going down. Then the highest point or the maximum point of this wave are called the crests. So the distance between two crests, this one and that one, is the one that we call the wavelength, and represented by lambda. Yeah, so this distance here is the one that is called the wavelength. Alright, so let's quickly look at the wave velocity. So this is just the rate of change of displacement of the wave. So when you talk about the rate of change of something, it means that that thing has to include something that has to do with time. So the rate of change of displacement of a wave. So displacement of the wave changing with time is called the wave velocity. So this one can also be written in terms of the period and the wavelength. So when one wave makes a complete when this distance is the wavelength in short, or a wave is complete, in other words, it means that this becomes what is called the wavelength. And then the time that is taken for one complete wave is called the period. So meaning the time will also change to period, and we know to say wavelength over period is also the same as velocity. So now when you look at this, remember what we said. We said frequency is simply given by 1 over t. So meaning this side where there is 1 over t, we can write this part as frequency. Hence we can just have the velocity being given by wavelength times frequency. So the velocity of a wave, or of a wave or a complete wave, can also be written as f lambda, which is just frequency times wavelength. Okay, let's also look at what is called intensity. So this is just a time rate of energy transfer by the wave per unit area. So we're also going to look at this in the next lesson that we're going to have. We'll look at it in details. Okay, let's discuss the wave velocity, and of which I believe I've explained this on the previous page. So velocity is just given by displacement over time. So displacement is simply x, and then time is simply t. Then when we talk about that in terms of so the displacement covered by a wave is equal to that, the wavelength, and then when t is equal to the period. So this gives us this, which I've already talked about, and also leads us to finding this as the formula for velocity. Alright, so in the above equation, the above equation is called the wave equation, where lambda represents the wavelength and f represents the frequency. Okay, so speed of waves on strings. Let us also look at this. This one I'll just show you the formula. I will not be able to derive it today. We may derive it on another topic, but for today I think let's just look at the formula. Okay, so for a horizontal fixed for a horizontal string fixed on one end under the tension F, the speed of waves are given by the equation, this one. And then from there this one is called the linear density, and then this one is called the tension or the force in the string. And then this one is the linear density, which is just the string, the mass of a string per unit length. So linear density is given by the mass of a string per unit length. So if you put it there, it means that you can have something like this. You can have the force there over mass per unit length, which can also be written as, when you divide this will be F L over M. So this can also be simplified when the tension there. Okay, let me just end here. I wanted to introduce something else on the tension, but let me just end here. So sometimes you can just be given the tension, the length of the string, and the mass of the string. You'll be able to find its velocity just using that, because you know that this mu here, which is just the linear density, is given by the mass over length, over the length of the string. Right, so this is the end of today's slide. Thank you very much for attending tonight's lecture. See you in the next lecture that we're going to have. Shalom, shalom.